Hi, in this video I hope to explain how integration leads to the surface area of a function. For that I will draw in two functions in a graph. Y is 2x and y accent is 2, so that's the derivative of this one. Alright, and I assume you know how to calculate a derivative. Integration is basically a form of counting. Because if I say count to 4, you would assume a 0 and add up once until you arrive at 4. Integration is similar. You start at the bottom of your integration interval, so 0 in this case, and then add up little steps of x until you arrive at 4. So I don't care about how many steps I have to take, I just know in the end it will be 4, so by definition I arrive at 4. This can be written as follows, right? 0 to 4 as my integration interval, the steps I take, and then in this case I will get a value of 4 seconds. Alright. And I'll do a short recap on differentiation, what it means, all you need to know. And function increases with value, and that increase can be characterized by a differential. So the differential gives the ratio of change of y with respect to the change in x. So if here it's 2 all the time, which means that if I have an increase of a half, like I have here, then I would get an increase of 1 in the y direction. An increase in x of 1.5 would give an increase of 3 in the y direction. Alright. While we are integrating, we have different options we can do. We can just take the steps itself, and then you would end up at your end value of x, right, 4 seconds. But while we're taking these steps, we can also multiply by the differential of a function. Right? So if I want to integrate these delta y's over delta x, so the differential with x, then I would have this formula, which means that every step I take, basically I can cross out these out against each other and would just add up delta y's. Alright, and you can actually see it as such. So delta y. Don't write it as like this because it's confusing. You would think you were integrating over the y axis, but yeah, so don't write it, but it is what you're doing. You're just adding up y's until you're at the end of your x interval. Right, so you can just plug in the value of 4 in the primitive function, right, if you do this. So the primitive of this delta y, the primitive of this differential, right, which is y is 2x, and you will get, in this case, 8 meters. Another thing you can do is you just multiply delta x with y. Alright, so every time you get this little slice of surface, so you add up surface areas, right, until you're here at 4, x is 4. So then you would integrate a line element into a surface, right? The line element being this value, right, times delta x, and you would get a surface area. But you can't really do any plugging of values into functions here because y is changing on you all the time, right? So we have to find something different for this. For a moment I will just swap things around and assume this is the function we want to calculate the surface area for. Well, I have to color this blue, I forgot. And we integrate, so basically the value of p, right, over the axis until you are at 4. So you would arrive at 8. You can just see that 2 times 4 is 8, right? But that only works because we have a nice rectangle here. So let's have a more rigorous approach to it. So we multiply p by delta x every time, like here. We can't calculate that, but what we can calculate is its equivalent, alright? And you could, instead of calling it p, right, you could also call it dy divided by dx. So because it is y-accent, right, it is the differential of this function. And then you would arrive here at this point 8 meters, alright? So this is how the primitive constitutes the surface area of its derivative. Now, this holds true for any function, because here it was just one straight line with one tangent line, right, lying on top of it. Yeah, you had a constant differential, right? But this could of course also be part of another function, right, like this. And and in this interval, right, this delta x interval, this would hold true, right? So right, let me try it here. So this would be the surface area from here, and then this if this was the primitive, right, of this function, which it is actually, within this interval, then you would add this much surface area given by the increase in this function, right? But it has more tangent lines like this, so again, right, here you would have a higher value for the tangent line, right? And then you would also add up more to this function, right? So it would just go out of its straight path to form a new tangent line, right? From this it is clear that the primitive develops in value while it is recording the surface area of its derivative. Alright, and now we can also do it the other way around. So let's call this the derivative. So y is 2x, this time is the derivative of another function. And let's call that function z, right? So this function could be seen as z-accent, alright? Then we can integrate, and we then do the opposite as we did with differentiation, and we will get the function z is x squared, which is the primitive of this function, alright? And now I can say, okay, integrating my y value here, so integrating from 0 to 4, alright, my y value while taking little steps of x is equal to integrating the differential of x squared. So the differential of x squared is dz divided by dx times dx. Right, so these are the same. So now I know I can plug in that 4 value into my z function. Alright, and that is 16. Alright, so yeah, that gives me the surface area of what is under the y is 2x function up to the point that I'm at x is 4, and that would at the same time be the value of z for this function.